Hey, sixth grade, here are your video review notes for the plate tectonics quiz. Remember, watching these notes is not enough. It's good to review. It's good to make up if you missed some notes in class, but remember, when you review, you need to make something. You need to make flashcards, you need to make extra review pages, you can make notes of your notes, or you can make your foldable. That's the best way to review for this quiz. So, plate tectonics. Here are some of the essential questions that got us started with plate tectonics. Leading into it, the first idea about plate tectonics came with this idea of continental drift. It's this theory that the continents are drifting, all right? And there were four sets of clues that helped Alfred Wegener come up with this theory of continental drift. The first is that if you look at the continents, they're kind of shaped like puzzle pieces. Like this is the edge of a puzzle piece, this is the edge of a puzzle piece. Perhaps if they're sort of shaped like puzzle pieces, perhaps the continents were once closer together and actually together as one big continent. That's the first one. The second are similar animals, so that there were similar animal fossils found in different continents. There were similar fossils found in South America and Africa. Thinking, well, if there was the same animal living, did they really just travel all the way across the ocean? Or perhaps were these two continents once closer together when that animal lived, and then they died, became fossilized, and that since then those fossilized rocks have split apart? That brings up the third one, is that there's similar rocks and similar sort of mountain ranges made of similar rocks. And those are, good example of those are found in northeast North America and in the sort of northwestern part of Europe. And these similar rocks were found there. They're very similar types of mountains. It's like, well, maybe these also were once together. And the third piece of evidence, and it sort of says it up here as well, all right, were tropical fossils. It has to do with climate. Tropical fossils were found way down here in Antarctica. Antarctica is a very cold place today, so how in the world could there be tropical fossils there? That must have meant that there were once tropical plants there. How could there have been tropical plants in Antarctica where it's so cold? Well, perhaps Antarctica used to be closer to the equator and has since drifted down there. So these four pieces of evidence point to the continents drifting, but the thing that Wegener couldn't prove or couldn't really describe or explain was, well, why? Why are they drifting? And people didn't really still believe him with that. Then comes World War II. With World War II, between many countries in World War II, but two of which were the USA as part of the Allied power and Germany, part of the Axis powers, and we were against each other, and we were sending submarines back and forth over the Atlantic Ocean. Submarines were using a new kind of technology called sonar to help figure out if they were going to go and run into mines or figure out where there were other submarines, and also figure out if they're going to hit the bottom or not. And as they were doing that, they realized every time they crossed over the Atlantic, they'd find this ridge at the bottom of the ocean. They realized no matter when they crossed over some part of the Atlantic, always about in the middle they crossed over a ridge, and this was interesting. Then the war ended, and scientists realized, well, let's try to use this sonar to get a better picture of all the different parts of the ocean floor. If there's a little bit of a ridge running through here, perhaps there's other things going on in other parts of the ocean. So they did that, and throughout the 50s they did, and sure enough, here's what they discovered. There's all sorts of stuff going on at the bottom of the ocean. Yes, here's that mid-ocean ridge that they saw, but there's also sea mounts, these kind of little mountains underneath the sea, all sorts of things like that. Now, once they were able to see this, and through a couple other pieces of evidence, such that the rocks near the middle of the ocean are younger than the rocks near the edge of the ocean, they had a new theory that the seafloor is spreading. So Henry Hess was the one who figured this out. The seafloor is spreading apart. Well, if the seafloor is spreading, that could mean that the continents are sort of drifting with it. The sea is getting bigger. That's what's moving the continents around. These two ideas coupled together created this new idea, this new theory called plate tectonics. So continental drift, the idea of continental drift, combined with this idea that the seafloor is actually spreading apart, led to this new big theory of plate tectonics. This theory that the Earth's crust is made of plates. Those plates are kind of floating on this liquid layer of magma called the mantle, and that those plates are moving around. We look at the inside of the Earth. Oh wait, we're getting ahead of ourselves here. Now wait a minute, time out. If the continents are drifting, kind of working backwards, does that mean that they were perhaps once all together? Sure enough, that's what it means. And in fact, there's a word for this supercontinent that existed that 250 million years ago. This was Pangaea. It was at the beginning of the age of the dinosaurs that Pangaea started to split apart. So during the dinosaur age, there was a little bit of the Atlantic Ocean, And then once the dinosaurs became extinct, we head into the Cenozoic era. The Atlantic Ocean is still moving out, coming apart. But if you kind of go back in time, these are what the continents looked like about 250 million years ago. And we'll learn later on, when we do geologic time, there were other supercontinents even before Pangea, way back billions of years ago, which is kind of neat to think about. All right, but wait a minute. Back to these moving plates. What makes them move? The answer is convection currents. Because there's a heat source deep inside the Earth, that causes some magma to get really hot. It's all hot, but like really hot magma to rise up. Once it gets higher away from the center of the Earth, it cools. And once it cools, it sinks. There it is sinking. It sinks back down, then it warms up again and rises. And we saw that in our little convection demo that we did in class with the water and the fish tank, where one side was heated up and we could see the water moving in a convection current. And we put that piece of wood floating on top of the water, and because there was a convection current moving underneath it, it moved the wood along. And this is what happens inside the Earth. The center of the Earth is solid. It's called the inner core, and it's solid, and it's hard, and it's super hot, made of dense materials like nickel and iron. And then outside of it is what we call the outer core. It's liquid, and from that out comes a whole lot of energy. It's coming out, coming out. So the whole inner core and outer core, super, super, super hot. Then you have an area called the mantle, and it's in this mantle that convection currents occur. And as they spin these convection currents, kind of like conveyor belts, they move the crust and the plates of the crust on top. And if there's a place where two convection currents, see here, well, this is coming up and this is coming up, it could split and pull away two pieces of crust, two plates. You might get an ocean in between. Perhaps there's a place where the convection currents are turning such that they're bringing this plate coming together and this plate coming together. You can get mountains where two squish in. So it's this moving convection currents that moves the plates on the surface of the Earth. And those moving plates can create lots of interesting features and dynamics. Here's another example, another picture of that. Inner core, outer core, convection currents in the mantle that causes either plates coming apart or plates coming together, and sometimes plates sliding by each other. This slide you don't have to worry about too much. This is just sort of shows, relatively speaking, the relative highest point of the Earth, the deepest point. Don't worry about these words here. Just relatively speaking, remember that overall the Earth is pretty smooth. Though yes, Mount Everest might seem high, and the Mariana Trench, the deepest part of the ocean, might seem pretty deep. Relative to the extent of the entire surface of the Earth, they're not really that high and that deep. But don't worry so much about that one there. So here we go. When we look at all these, here comes the different plates that we can see based off of these features. Where plates are coming together, we see more mountains, and where plates are coming apart, like here, we see mid-ocean ridges in the ocean there. Here's another picture, same idea of different color-coded plates. You do not have to memorize the plates, though do know that we're on North America plate, and there's the South America plate. Also note that plates can have sometimes continent types of crust and ocean type of crust on the same plate. Here in the South American plate, this part is continent crust. Over here is ocean crust. The Pacific plate made up entirely, almost all of ocean crust, whereas like the African plate, the middle of it has continental crust, but this part of the plate has some ocean crust. Now why is this? Oh, here's a big idea too. If you look at it, are we at the edge of a continent? Us here in Philadelphia. Yes, we're on the edge of the continent. Continent, right there, here we are, we're right on the edge of a continent because there's the ocean and there's the continent. But are we at the edge of a plate? No, we're right in the sort of middle, of the North American plate. We are not near a plate boundary. Californians, they're at the edge of a continent, they're at the edge of the land, but they're also at the edge of a plate. They're at the edge of both a plate and the continent. This is important when we come to what can happen at plate boundaries. Now, there are three types of plate boundaries. Ready? You know them. Divergent, convergent, transform. The first one, divergent. Plates are coming apart. Convection currents underneath move two plates that diverge from each other. We said before, an example is the mid-ocean ridge. It can also happen right in here. This is the East African Rift Valley, and that's a place where Africa is starting to come apart. And eventually that's going to be filled in with ocean water, and eventually it's going to be a big, big ocean over millions and millions and millions of years. So a divergent boundary is one type of plate boundary. The other kind of plate boundary is convergent. Convergence are when two plate boundaries come together. Now, a couple things can happen. When it comes together, one of those plates is going to be pushed underneath the other. And that's called a subduction zone. Think submarine. A subduction zone is one plate subsides underneath another. Now, what can happen at these types of plate boundaries depends on what kind of crust that we have. We have two types of crust, ocean crust and continental crust. First, let's see what happens when ocean crust runs into continental crust. Ocean crust, continental crust. The ocean crust is pushed underneath. In that, you get lots of friction and you can get earthquakes. The crust that goes down melts. The melted crust comes back up as magma and might reach the surface as a volcano. So you can have volcanoes. And the fact that one of the crusts was ocean, there's an ocean nearby, you can have a tsunami where an earthquake happens and moves the water in the ocean and create a tsunami. So if you live at a plate boundary between ocean crust and continental crust, like if you live near the Andes, you could experience volcanoes and earthquakes and tsunamis, all right? There's also an ocean trench right in where, see the deepest part there, an ocean trench where the plate is sliding under the other one. That's the deepest parts of the ocean are in ocean trenches. So that's one type of scenario, like the Andes Mountains. Another type is what if we have an ocean crust hitting another type of ocean crust? Well, one of those two ocean pieces of crust will go underneath, and again, you can have lots of earthquakes as they rub along faults and can create lots of earthquakes. And because you're near the ocean, you could have tsunamis associated with those earthquakes. That earthquake could move the ocean and create a tsunami. You also have the trench there, just like before, with one going at the other. And again, you can have where the crust melts as it gets lower down, comes back up, sort of bubbles up as magma, reaches the surface, you can have a volcano. Japan is a great example of this kind of convergent plate boundary between two pieces of ocean crust. And Japan has volcanoes and earthquakes and tsunamis. There's a lot going on there. The third type of convergent plate boundaries, if you have big continent crust hitting another piece of continent crust. Now with these, you have lots of earthquakes, that's for sure, because there's lots of collisions going on, lots of rubbing. But you don't really have volcanoes, and because there's no oceans around, you don't have tsunamis associated with the earthquakes. But you do have big, big mountains. All of these types of convergent plate boundaries can give you mountains. You can have really big mountains here. The Himalayan mountains, including Mount Everest, are a good example of this continent crust to continent crust convergent plate boundary. Finally, the third type, transform, is when they're not coming apart and they're not coming together, but they're kind of like just sliding past each other. And this can happen. A best example of this is the San Andreas Fault. A fault is sort of a big crack in the crust and the rocks of the Earth. And when those, along that crack, if the rocks move and if the whole continents move, sliding past each other, they can release earthquakes. So at transform plate boundaries, because you're not having sort of a collision or a pull apart, you don't necessarily have mountains, but you do have lots of earthquakes. There's lots of rubbing along there. So if you see here, this side of the Pacific plate's heading this direction, the North American plate sort of sliding down in this direction here. That's why there's lots of earthquakes in San Francisco and Los Angeles. Okay, that's the end of our notes there. Oh, please also know, as part of the Google Earth activity, we plotted the locations of volcanoes and earthquakes. Please practice plotting. Make sure you know how to plot. If given the latitude and longitude of an earthquake, could you put it on a map? And to note that how those volcanoes and earthquakes show you that they happen at plate boundaries. Where you find earthquakes and where you find volcanoes, most of the time, not always, but most of the time, earthquakes and volcanoes occur at plate boundaries. So if you figure out where earthquakes and volcanoes occur, you can have a good picture of where the plate boundaries are. All right, that's the extent of the notes. Always check in with me if you have questions. Send me an email. That's totally fine. Come by at Extra Help. Totally awesome. That's it. See ya.